Hi, my name is Thomas Kim. In this session, we will learn auto-sorted vector. Past search using binary search, we can test whether some element belongs to the vector. And past retrieve using std lower bound. And key value bidirectional search is possible when you use this implementation. Also, we will use optimized memory use. Not a single byte will be wasted, and we can allocate large chunk of memory instead of allocating small strings. All these things are possible if we understand how to implement auto-sorted vector. This session continues from my previous video, fast search for elements from vector. Please download the source code by clicking this link if you want to follow with me. In your download folder, unzip it, then copy the solution to your working folder. Now open it in Visual Studio. We will add a new project. We insert it to console application. Auto sorted vector. Console application, finish. Right click, start a project, and past search iterator, double click it, Control A, copy, then auto sorted here, paste, scroll up, then remove this part, then Control F5. Okay, this is the state of our previous video, source code we developed in our previous video. I will make a few tweakings. This is the state we developed our code in previous video. So if you understand or follow with me, you probably have to watch my previous video. So here, one of my viewer, I forgot his name, suggested that there is some other way to implement this lower bound algorithm. And I have been thinking, then I have tested. Then this index is currently pushed here. And I found this index 2 is the same index, this index. Okay, so I will display index like this. Search index, then search index like this. And also while searching lower bound, I put message like this: idx1, idx1, idx2, idx2, std, and then if we run it, Control F5 once again, we can find that search index is 5. This idx2 in this lambda function, idx2 is actually the search index. So we can change it like this. It can be anything actually. We can remove it anything, just any dummy index. Then instead of doing this, we can change it like this. here we will be accessing search index like this. Then here we can just simply change it like this. And we will change it to something like James. Here instead of Stephen we will put it James. Now Ctrl F5, run. It is not search index, this should be search text, okay? Search text, sorry. Like this. Then Ctrl F5, run. So the result is the same. We found James like this. And also I want to remind you one thing. Say here we can change like STD, cout, index, ITR. There is two kind of index. Another index is, I say, VCTR index. ITR indices, BEZIN. I will change it like this. Okay, now let's run it. So here if we see it, VCTR index is 3 and index is I will modify this code once again for easy understanding. Before sorting, we will display all information. Then names, then we will not need this. Copy, paste, copy, paste. After sorting, also okay, now let's run. So it gives all information. Before sorting 0, 1, 2, 3, this is array index. vector index, and this is index contents. Then this is unsorted. These are unsorted like this. After sorting, this index doesn't change. This is fixed one. This is actually memory address, and this is the contents of indices are changed like this. Then here Alice, Betty, Charlie, James, Sophie, these strings is sorted, all sorted. So you have to watch this, how these names are accessed carefully. And for example, it means zero. Say when zero, the first here, when zero means this is the first element. Okay, so first one, 3 means please refer to this address 3. Betty is displayed here. In third case, this is first, second, third. So number 4 means this address. Please watch my mouse pointer carefully. Means Charlie. So Charlie is displayed. In this case, 1 is this element. So James is displayed. Lastly, 2 means to this address, Sophie is displayed like this. So in here, James is found from name means, say vector index is 3. 3 means this. This is 3 means this here. 3 means here. This index is here. Vector index means 3, and this value is 1. This value is 1. It means access to 1 here, so it is James. So James is searched like this. So understanding this layout is paramount to implement our code. Okay, so now I will change it one thing more. So this is current state. Then we can change searching like this. We don't need to put. We will keep this one, but we don't need to do this. We can remove now these things. Save. Then here we don't need to we have to remove this now because we haven't added anything yet. And the remainder is the same. And also we have to remove this like this. Save. Also from our previous code we have to remove these like this. Okay, and I will put the same text once again here. In this case, text exists. Such text is in the container. In this case, such text is not in the container. Okay, not in the container, and gives us the position. We can insert such text in order. Okay, so if we find this condition, then we can insert such text, and this is also the position the such text does not exist. Such text does not exist in the container, and we can push append at the end. Okay, so you have to understand these things. I will show you very soon. So we will run it once again, then I will explain. So please read the Alice, James, Sophie like this. And we found James from name. If we found James, it is coming from this message, from this part of code, from here. So if we found James, we don't need to insert again in this vector. But if we don't found at this line, we say Stephen. We will change it into Stephen, Steven. Then let's run it. Then search index 5. I need to make more changes here. Sorry. Here I removed it, and I will also okay, I will do like this. In this case, in this state, Alice, James, Sophie, Charlie, Stephen is out of range. In this case, we can simply add at the end of the vector. I will handle this case first. So we can simply add in the size t, new index, indices, size. Okay, then we can push back indices, push back new index, and we can add names, push back. We can simply push back search text like this. Then we will display this code once again. Display. We will put after inserting. We will display here after insertion solution. Then the code is the same. Now let's run it. So this is flat before sorting, this is after sorting, and we now try we search for Stephen, but Stephen is out of range, so we insert Stephen at the last here, then it is all sorted this way. Okay, now we will search for, so we will run it once again, then we will add bongo. This is Betty, so we will add bongo or bango. We will add bongo or bango. Here, search text will be bongo. Now we will learn it. So bongo can be inserted with the Charlie. Okay. So index 2 means here. Index 2 means vector index 2, 0, 1, 2. Okay, here. Let's see, 0, 1, 2 here, probably 0, 1, 2 here after sorting here. So 2.4. Okay, 4 2. It is pointing 4 here. It's pointing Charlie, so Charlie is displayed. If we want to insert, I will insert in primitive way. Then here, now we will push names, push back search text. Okay, and also need to insert one indices. Pushback 0 is dummy. This 0 is dummy. It will be reset. Okay, so it's not important at the point. It is just we are just appending 0 to make room for one more element for search text. Okay, so then we have to reset size t, size, say indices size, like this. Then we have to reset the indices for size ti 0, I size plus I, it should be size t. Then indices I equals I. We are just simply resetting indices. Okay, we simply reset indices. Then we have to sort again. Where is the sort? Okay, here we sort again. We have to sort again. We have to sort again. Now let's run it. Okay, in this case, in this state, we inserted bongo at the last line. Then we sort again. There is some problem. I have to set it I. Let's run it. Okay, so this is after sort, before insertion. This is before insertion. Say if we are going to insert the bongo, then it gives vector index 2 means this one. This is number 4. 2 means this index, 4 means 4. This is after insertion. Alice, Betty, bongo, Charlie, like this. This is new insertion bongo. Okay, so at this point in index 2, vector index 2, the last new index should be added. Okay, should be changed like this. It should be in this state. This is newly added. Sophia, previously it was 4, but don't think about this number. We have to change the last index to index 2 here. So currently it has its last index is 4, then the next one is 5. So in this 2, in vector index 2 here, we move to here. Then the next one is 5, so we have to set it 5. Okay, then after this we see 1 2, we have to put down, move down the indices. Okay, so this 1 2 means this 1 2, 4 1 2, 4 1 2. These all three indices, this index is 2. These all three 4 1 2 should move down, 4 1 2. And this one, the tooth index should be the next largest one, 5. 5 should go into this place. Okay, so we will change this way like this. Please try to understand this part. I will explain once again. Bongo can be inserted before Charlie means it gives index 2, vector index 2 here. vector index 2. So the next largest index is 5. Okay, we are going to insert 5. So we have to put 5 here, 5 here. We move down 4, 1, 2, 4, 1, 2. We move down. Then we put 5, the largest one here. So I will implement it. Now here, please note that we have to remember the size here. Since we declared this is search index. Search index is actually not needed. We will say we don't need this search index. I will say just the size, last index. Okay. I will say new index here, new indices before search bound, and here we now have to insert or we can just move it here. We don't need it here, so we can just copy and move it here. Sorry, X, paste here. Then please note that we are going to insert the last element. Before we insert last element, we have to remember the index we found. So we will do like this: size t, index here, itr minus indices begin. We are calculating begin. We are calculating index relative offset of address is index. Okay, then we push back like this. Indices, we have to make room, indices, and push back 0. It can be any number because it will be overwritten. It can be any number because it will be overwritten. Okay, overwritten. Now we move down for we will have new size. No, we can just do like this. For size t I, we can use like this because we inserted it is valid because we inserted one element. This is the previous size before insert, so this is valid. And then I should be greater than this index, right? This offset. I will say start index, changed index. Okay, so I can put it here. Then minus I. Then we are now moving down the indices like this. Indices I equals indices I minus 1. Okay, we now moved all indices. Then we change indices, changed index here. We put the last one like this. Okay, then it's done. Now let's run it. Now we don't need these things. since we need another thing, we have to push the names, push back, search text, okay, then it's done. Then we don't need this, then we don't need to reset, we don't need to sort. Okay, I remove everything, I just display after insertion. Okay, now let's run it. Okay, please remember we inserted the bongo. Say Alice, James, Sophie, Betty, Charlie, Alice, James, Sophie, we inserted the bongo here. But when we display Alice, Betty, bongo, Charlie, James, Sophie, it is after insertion. This is before insertion. If you compare this sorting, please note that when we search this index, it returns index 2 search index. Then it becomes we are putting bongo before Charlie. Charlie's index is 2. Okay, so in 2's place, the next largest one is 5. In 2's place we put 5. Then we pull down. We first pull down 4 1 2 4 1 2. We have to pull down like this. So this way we can always maintain sorted how can I say, sorted vector. For example, if we can insert once again, if we want to insert another text like this, we will copy all this part. This part, I will copy the whole text once again, then paste. Now I will say this is first bongo, then I would say golf. Okay, golf. Then golf will be inserted and sorted. We have to remove like this, search text. And also oro should be removed, I think. And let's see. Okay, let's run Ctrl F5. So we inserted, this is before sorting, we inserted bongo here, bongo golf, and golf is sorted like this. Alice, Betty, bongo, Charlie, golf, James, Sophie, every elements are sorted automatically. This is very powerful way to insert and sort automatically. Please note that we are not actually moving or copying the strings. We are only sorting the indices like this. So it's very fast algorithm. If you ever compare the set or map with vector, you must have noticed that vector is very fast. SDD vector is very fast, and there is one very good reason why vector is so fast than set or map. Because in case of vector allocates big chunk of memory, not just one by one, instead of big chunk of memory. So vector does not need to allocate very frequently. But in case of set or map, whenever we insert a new element to set, every element that new element should be dynamically allocated each time. So that's why set and map are so slow compared with the vector. Using this algorithm, in next session we will make this, what we learned in this session, into a complete class, auto-sorted vector as a class that we can replace using set or map in a much more efficient way. Also, if we implement our map and set as in map and set, I mean SDD set, SDD map, and also SDD multiset, and SDD multimap. If we can implement all these things with our vector class in what we learned in this session, and if we implement this way, key value are bidirectional search over. Bidirectional is search over. Okay, so our algorithm, our method will be much more efficient than standard library set and map, multiset and multimap. In my next video, I will implement these what we learned in this session into a complete class. Thank you for watching.